Hello everyone, so today I have a really cool question on the floor function of the roots of an equation. So this question does not require a very high level understanding of the floor function, which is also called as the greatest integer function. And really the introduction that I give you at the start of the video, before the start of the problem, really, I think that would be pretty much enough. So we're going to explore a little bit of the floor function is, and more importantly, this is just going to be a really nice mixture of algebra and a little bit of calculus. So let's begin. So this is the problem number 3 from the Indian National Math Olympiad in the year 2004. And in this video, we're going to be looking at the greatest integer function of the roots of an equation. Like I said, the greatest integer function is the thing with the floor function. I'll elaborate a little bit on that later. After that, we have strictly increasing functions. Then we have the book sessions for the INMO. And at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so they are saying that if a is a real root of this equation, right, x raised to power 5 minus x cubed plus x minus 2 is equal to 0, then find the value of the greatest integer function of a raised to power 6. So what is the greatest integer function? Well, greatest integer function of x, what is called greatest integer function, GIF, also called the floor function. It's also called the step function. It has many names, but the most common names are the GIF, greatest integer function, and the floor function. So what does this do? It is basically the greatest integer. So it is the greatest integer that is less than or equal to x, right? So what does that mean? It means the floor of x is less than or equal to x, and it's the greatest such integer, so it will be greater than x minus 1. Let me just give you an example. Like, this inequality doesn't make sense a lot of times. So basically, for example, what will be the floor of 2.3 or the greatest integer function of 2.3? Well, it's the greatest integer that's less than or equal to x, so that will be 2. Similarly, the greatest integer function of 7.9 will be 7, right? The greatest integer function of maybe 10.1 will be 10. Right, the greatest integer function of, let's say, 9.151, whatever it can be, this will be obviously 9. So if you can see the pattern where it's stepping down, so essentially you kind of ignore the things after the decimal and just step down the value a little bit, and that is essentially what this inequality over here is trying to say. And this is actually a very important property of this, and you'll actually directly have this application in many questions. Similarly, what's the greatest integer function of 3? It'll be 3, right? But the greatest integer function of x is less than or equal to x. It can be equal to x. And essentially, greatest integer function of an integer k is just k, where k is an integer, right? So that's just simply that. Now, maybe if you go on to the negative numbers, or maybe let's just draw a number line. So 0, 1, 2, 3, 4, minus 1, minus 2, and minus 3. And this extends obviously. So if we have a number, if we, let's say, I consider x maybe 2.5, so it'll be something over here. So what's this greatest integer function essentially doing? It's stepping it down to the previous value, right? The greatest integer function of x would be 2. But now, if I maybe consider x is equal to maybe negative 0.5. So it's over here. What will be its greatest integer function? Will it be 0? No, because we want the number that is less than or equal to x. 0 will be greater than negative 0.5, guys, right? So it has to be negative 1, because negative 1 is less than this quantity over here. Similarly, if we have, let's say, the greatest integer of negative 7.9, it will be negative 8 and not negative 7. Because on the number line, for example, we have, let's consider negative 6, negative 7, negative 8, and negative 9. We have negative 7.9 over here somewhere. So its greatest integer function, and we have, let's say, 0 over here. So we need a number smaller than this. So it will obviously be negative 8. Negative 7 would be greater than that. It cannot be the floor function. So I think that's a good introduction to floor function. But anyways, maybe let's return to the question. So in the question that they had given this, that f of x is, let's say, a function that is x raised to the power 5 minus x cubed plus x minus 2 is equal to 0. And if, let's say, a is a root, so f of a is equal to 0. And we had to basically find the greatest integer function of a raised to the power 6. Right? So how can you proceed with this? So maybe let's just try and find f prime of x. Like maybe just like differentiate this function. You'll get 5x raised to the power 4 minus 3x squared plus 1. And when I see that, I notice that this is like actually strictly increasing. It's a monotonically increasing function. And how do I kind of determine? Well, it's pretty easy because this can be, just factorized, or maybe like just completing the square. So you can just write like this, and you can see that this is always greater than 0. There are ways to do it in calculus as well, but you can just complete the squares over here. So what is this quantity? So 2x square minus 1 whole square plus x square plus x raised to power 4. This will obviously greater than 0 because this is sum of squares, right? Sum of squares is always greater than or equal to 0. It can be equal to 0 when all of them are individually 0. When do these guys become individually 0? For example, this is x equal to 0, x equal to 0, done. But if you put over here x equal to 0, it will not be equal to 0. It will be actually 1. Similarly, if you have maybe 2x square minus 1 equals 0, or x equals to plus or minus 1 by root 2, if you put this value over here, then that won't be equal to 0. So we can clearly see that this is always greater than 0. It can never ever be equal to 0. So that essentially means that f prime of x is greater than 0 for all x belongs to real numbers. Therefore, we can just conveniently say that f is increasing. And in fact, it is strictly increasing. Because that's an important thing for us. Okay, so maybe just move on. So what can we say about the roots of f? So for instance, if it's a strictly increasing function, let me just maybe make a graph, right? So for example, it will be something like this. It's a very rough graph obviously, but it will be something like this. Essentially, it means that it can have only one real root. Right? And this is very important because in the question they're given us real roots. And this is actually very influential. And why is that influential? Because the only root is a, right? So the only root is hence a, right? A is the only root over here. And the reason why this holds true is because once f exceeds 0, it will never be less than 0. For a root to occur, you need to go from, let's say, negative to positive if it's an increasing function, and positive to negative if it's a decreasing function. Let me just draw it graphically. So this is an increasing function, slope positive. This is a decreasing function, slope negative. This is the positive region, and this is the negative region for the y-axis, obviously, okay, not for the x. So this is the negative region, and this is the positive region for the y-axis. Now that is essentially what we are seeing. If it's an increasing function, going from negative to positive, and if it's a positive decreasing function, it's going from positive to negative. And we can very clearly see that the root is only when one of the signs are interchanged. It's a very elementary concept in calculus, but anyways. So basically, if let's say our function f, if f becomes greater than 0 for some at x1, let's say at x equal to x1, right? And then we have it, so it will always be greater than 0. Then that implies that f of x will always be greater than 0 for all x greater than x1. Does that make sense? Yeah? Because it's obviously increasing, strictly increasing. It will never ever drop down to maybe come back like this and then again intersect a root. This will never happen. So this has only one root, and that is a. I think that's pretty clear. So what was f of x, right? F of x was x raised to power 5 minus x cube plus x minus 2, and we see that it has only one real root, which is a. Now maybe let's just find out the value of f of 1. So what is f of 1? It will be 1 minus 1 plus 1 minus 2, which is obviously minus 1. And if I find out f of 2, that will be 2 raised to power 5, 16 minus 8 plus 0. So how much is that? Okay, sorry, 2 raised to power 5 actually 32. So f of 2 is actually 24. It doesn't really matter, guys, because we now know that if f of 1 is a negative value and f of 2 is a positive value, that means a belongs to 1 to 2. And why can I say that? We'll look at here. If the function is something like this, we know that it's an increasing function. It looks something similar to this. If this is x equals to 1, and if let's say this is x equals to 2, we see that x equals to 1 is corresponding to a negative value. Similarly, x equal to 2 is corresponding to a positive value. So the root will be somewhere over here, right? Root, where is the root? Where the like graph cuts the x-axis, right? So the root a will be somewhere between 1 and 2. That is why, therefore, I wrote a is between 1 and 2. Great. Now maybe let's just calculate f of 6 by 5. Just plug this into the function and you'll get minus 124 by 3125. And when you plug in f is equal to 5 by f of 5 by 4, you will get, I believe, 357 by 1024. So again, this is negative quantity, this is a positive quantity. Therefore, a lies between this 5 by 4 and 6 by 5. Right? Or actually the other way around. Because 5 by 4 is greater, obviously. So a essentially lies between 6 by 5 is, I believe, 1.2 and 5 by 4 is 1.25. So it's very close actually, right? A belongs to this, 1.20 and 1.25. So you've dropped down the value of this, right? A lies between what, 6 by 5 and 5 by 4. Now let's find out the value of a raised to power 6, because that's given to us in the question, right? Raise this to the power 6. What will you get? A raised to the power 6. And this will actually be like approximately like 9.8. And this is in fact 156254096. And this quantity is obviously less than 4 because 4096 into 4 is something in the 16,000s. And so obviously that will be less than 4. So we get this very interesting result that A raised to the power 6 will be greater than 2.98, will actually be less than 4. That what does that mean? It means that the floor of A raised to the power 6 can only be 2 or 3. Right? Why? Because if let's say maybe A is, let's say what? A raised to the power 6 is, let's say 2.99. So the floor of this A raised to the power 6 will obviously be 2. But similarly, let's say A raised to the power 6 is something like 3.5, right? It's still in the range, right? So the floor of this thing would be obviously 3. So it can be either 2 or 3, we don't know. So we need to work with the function a little bit more. So we had this thing A raised to the power 5 minus A cube plus A minus 2 is equal to 0. And let me just maybe try and factorize this. I'll get A raised to the power 4 minus A squared plus 1 is equal to 2. And they're actually very familiar to me. Why? Because I remember a factorization that looks similar to this. And I multiply by A squared by 1 and I divide by A squared plus 1. This is why algebra is like a little bit interesting. So what does this numerator become? This is actually nothing but A raised to the power 6 plus 1. If you study binomials, this will be pretty clear to you that A raised to the power 6 plus 1 has a standard factorization that looks like this. It can be easily factored by like A cube plus B cube. But okay, anyways. So A times A raised to the power 6 plus 1 divided by A squared plus 1 is actually equal to 2. And the reason I kind of multiply this A squared plus 1, the intuition was that I would get A raised to the power 6 in the numerator, which is beneficial to me. I need to find the floor of that, right? Now, we know for a fact that A minus 1 whole square will always be greater than or equal to 0, right? It's a square. So A square plus 1 will always be greater than or equal to 2A. In other words, A over A square plus 1 will always be less than or equal to 1 by 2. It's a pretty known fact. Now, if I multiply A raised to the power 6 plus 1 on both sides, I'll get this is less than or equal to A raised to the power 6 plus 1 by 2. But this quantity, A times A raised to the power 6 plus 1 divided by A square plus 1, this is actually over here. And that is equal to 2. So 2 is less than or equal to A raised to the power 6 plus 1 divided by 2. And if you just simplify this, I'll get A raised to the power 6 plus 1 greater than or equal to 4. In other words, A raised to the power 6 is greater than or equal to 3. What does that mean about the floor of A raised to the power 6? It has to be 3, right? Because we know that the floor of A raised to the power 6 can either be 2 or 3. But since A raised to the power 6 is greater than 3, for example, let's say 3 or 3.5, 3.7, whatever it might be, the floor of any of these values will obviously be 3. And from this condition, we can actually know that A raised to the power 6 can actually be like 4.5 anything from like 3 to infinity. But we know that the floor can only be 2 or 3, right? So that means the floor has to be 3. And I think this is a pretty interesting question because it involved quite a good concepts of algebra and calculus. So I really hope you learned something from that. Okay, so moving on, there's some book sessions for the INMO. Elementary Number Theory by David Burton, Problem Solving Strategies by Arthur and Gell, Functional Equation by Venkatachala, Problems in Plane Geometry by Sharagan, Elementary Number Theory by Sierpinski, Graph Theory by Harari, and Combinatorics by Brualdi. Okay, so at the end is a similar but challenging problem, and it's actually a very famous problem. I believe it came in the IMO shortlist for 1988. I think it was A3, but I'm not really sure. And I think this INMO question, this was to come in 2004, was in a way motivated by this problem. So this is probably the motivation for that question. And it's kind of saying that let A be the greatest positive root of the equation this, x cubed minus 3x squared plus 1 is equal to 0. Show that the greatest integer function of both of these quantities are both divisible by 17. So they are 0 mod 17, essentially. Over here, you're going to have to use something called as Vieta's relation. And apart from that, maybe try using a little bit of calculus if you can. And yeah, maybe try it out. And I'm pretty sure that the INMO problem was actually inspired by this. It's essentially like a simplified version of this problem, if you can put it that way. So you try this out. It's a very nice problem. And if you're able to solve it or make any progress on it, let me know in the comment section. And until then, I'll see you in the next video. Thank you very much and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.